Okay, our second mechanism for today is the mechanism for the enzyme class of serine proteases. So what we're going to see is some acid catalysis, some base catalysis, and our first example of covalent catalysis. Today will be an introduction to covalent catalysis, more to come in our next class. So this protein class, they are serine proteases, so they digest proteins. You can find them in our bodies for sure. They help us to digest the protein that we eat. And the reaction that we're going to see performed is a hydrolysis of the peptide bond. If you do any reading elsewhere about this bond, you may see it called the cis bond. That just refers to the bond that's going to be broken. And so in this enzyme class, we have a shared catalytic site among most serine proteases of serine, histidine, and aspartate. This is our catalytic triad. So this is what's in our catalytic site, also pictured down here below on the right-hand side of the screen. And one thing particularly interesting about this active site is that the catalytic residues and some other residues participate in a type of hydrogen bonding called low barrier hydrogen bonding. And what the result of this type of hydrogen bonding is that the pKa's of all three catalytic residues becomes nearly equal. So let's think about this for a second. Feel free to go ahead and grab your amino acid handout if you happen to have it handy. But you'll see that aspartate's pKa of its R group is going to be around like 3 to 4, right? Histidine's pKr is 6. And serine doesn't even have a pKr listed on this sheet. Why? Not because that hydroxyl group can't donate a proton, but because the pKr is so basic, it's just not physiologically relevant. Except we also know that the environment of an R group can impact its pKr. And so here is a real-life example of this concept that we learned way back when we first were talking about amino acids. When you get aspartate, histidine, and serine all together performing these types of hydrogen bonding interactions, their pKrs become nearly equal, which is super cool. So let's go through this mechanism for the serine protease catalytic site, starting, of course, by drawing the catalytic site. So we're going to draw our aspartate, our histidine, and you'll see again that I'm just going to simplify the R group and not draw it out, and also serine. Beautiful. Now, don't forget that these R groups are doing hydrogen bonding interactions with one another, but I'm going to leave that out of the drawing just because it can kind of confuse what's happening with the mechanism. So let's bring in our substrate. Serine protease's substrate is a protein. So I'm going to simplify this peptide, folks. I'm going to start the string of the peptide with R1, just assume that to be a bunch of the other bits of the peptide. And here is the first C terminus, then an N terminus, and then our alpha carbon, and then I'm just going to draw R3 as the continuation of this peptide, and then R2 here would actually be the R group coming off of the amino acid. So this is a simplified peptide, folks. What I want us focusing on here is the peptide bond that I've drawn. So the bond between one C terminus and the next N terminus from one residue to the next. Okay, now this mechanism is super cool, so let's jump right into it, knowing that our objective here is to hydrolyze this bond. So the first thing that happens is histidine, being a good acid-base catalyst, deprotonates serine. So it's going to grab that proton from serine, leaving us, rather than having that OH on the R group of serine, it's going to be O-. And so that O- is going to be a nice, strong nucleophile that can attack biochemist's favorite electrophile, the thing that looks like a carbonyl carbon, and in this mechanism, it is a carbonyl carbon. Carbon, of course, can only form 4 bonds, so let's make sure that we are drawing our mechanism correctly here, folks. Starting with the catalytic site, we've seen histidine is now protonated. But now, since serine performed that nucleophilic attack, it is going to be covalently linked now to our substrate. That carbonyl oxygen now is O-. And here's the rest of our substrate. Beautiful, love this. So if you think back to some mechanisms that you were learning in organic chemistry too, you might recall that after we have the formation of this tetrahedral intermediate with that negatively charged oxygen, the next step is usually to collapse that tetrahedral intermediate back down and to cleave a bond. Right now, we know we want to hydrolyze the bond between the carbonyl carbon and then the amine group next to it that forms that peptide bond. But if this NH just left when we collapse this carbonyl back down, it would be leaving as NH-, which is not a stable leaving group. So what we're going to do, folks, is when our tetrahedral intermediate collapses back down, we're going to cleave that bond off, and at the same time grab a proton back from that histidine so that our leaving group here is neutrally charged NH, which is nice and stable. So let's see what happens, folks. Histidine was deprotonated, so we are back to having a lone pair. Serine is still participating in this covalent bond with our carbonyl carbon. But now what you see is that we have lost part of this peptide that came in. So now we have broken off half of this peptide. But you'll notice that we cannot possibly be done with the mechanism because our catalytic serine is still forming this covalent bond to substrate. You know this is a hydrolysis, so let's bring in our good friend water to help us finish up this mechanism. And the second half of this mechanism is going to look very much like the first half of the mechanism. So we have histidine there. It's going to be a fairly strong base, and it'll be able to grab this proton from water. That leaves us with OH-, which is a great nucleophile that we can use to again attack the biochemist's favorite electrophile, the carbonyl carbon. Let's see where that leaves us. Histidine has again been protonated, so it's positively charged. We got our serine still covalently bonded to substrate, but again, substrate is now in a tetrahedral intermediate that is negatively charged on that carbonyl oxygen. So we're almost done, folks. If we collapse the tetrahedral intermediate back down, we can kind of see a path forward now where we can break the covalent bond between our catalytic serine and our substrate. And that would allow us to have finished the mechanism because we've cleaved the peptide bond, we've now performed a hydrolysis with water. Now we just have to regenerate our catalyst enzyme, catalytic site. So let's do it. If we collapse back down this tetrahedral intermediate, we can break the bond between the carbonyl carbon and the serine if that R group leaves as OH, because that is a nice, stable leaving group. And let's see where that gets us. Histidine has again been deprotonated. It acted as an acid and donated that proton. And now we also have serine back as well. It has been protonated. And we lost the other half of our substrate. Beautiful. Sorry, I can't get those lone pairs in. It looks like it's right at the edge of my screen. So this is the mechanism for a serine protease, folks. We saw acid and base catalysis. We saw that histidine was performing the role of both a base catalysis, grabbing protons either from serine or from the water that performs the hydrolysis, or histidine also performing some acid catalysis by donating a proton to make a better leaving group in the first half and in the second half of the mechanism. We saw serine doing a little bit of acid catalysis, giving up its proton to histidine so that it could perform a nucleophilic attack on the carbonyl carbon that it forms this transient covalent bond to throughout the mechanism. Finally, folks, we saw aspartate kind of just sitting around. We know it's participating in those low barrier hydrogen bonds that are important for this mechanism to happen. But we can also use our Coulomb's law thinking at different points in the mechanism. For example, let's take a look here at step 2. We see that aspartate is negatively charged, and since histidine accepted a proton, it is now positively charged. So in addition to performing those nice hydrogen bonds that help the pKa's become equivalent, we can see the aspartate doing some charge balancing here. So histidine is going to be really stable with its positive charge, especially when it's next to something negatively charged. Coulomb's law tells us that. So that's what we saw in this mechanism, folks. In the last video, we'll just wrap up talking about the serine protease binding site in addition to the catalytic site.